So we are looking at this survey article, and there's a couple of follow-up ones on here about Gaussian splatting. So it's kind of something that came up, I guess, here recently as an alternative way to visualize the neural radiance fields. It's not the concepts of splats and this type of primitive in general is not particularly new. The new piece is a couple different things. It's the neural network training to generate the scenes, and then it's also the directional components with spherical harmonics, which I'm not 100% sure if that's new or not, but it's the training of them with the neural network is. So basically, what they are is and he says it here. It's a bunch of blobs in space. They're a two-dimensional primitive. That's basically a flattened version of a three-dimensional Gaussian distribution in space. They can be extended on different axes and kind of become like from like perfectly spherical to something that is like I've seen some of the ones that let me there's this viewer that I saw here the other day. It's linked to in this article. They actually very interesting distribution of shapes that it actually uses. So if you zoom way in, you can actually see how they're kind of these little like needle-like shapes in some areas. But then it also gets lower frequency detail with yeah, I don't have a mouse on this machine, so it's navigating is a pain. But yeah, I would encourage you to take a look for yourself if you are curious about what specifically they look like here. And it's interesting in this viewer in particular, the thing picked up on a lot of these like background elements, and there's stuff like a block away, kind of, even though the focal object is just like the excavator piece. Yeah, this machine's not up to running that, but the idea is basically, yeah, we've got these flattened primitives that are basically you write a software rasterizer to draw a bunch of these. One of the things there, it's slight complication is the having to do a depth sort. So a lot of those are doing like a binning process, putting them like a screen space binning thing, and then doing the sort in tiles, so they don't have to sort as many of them. But so yeah, so they're splatted, and splat is this idea of like a screen space type of thing. They're not rendered as spheres. They're just this two-dimensional primitive here. So a lot of these are using the blending to do the like soft edges on things, because that Gaussian distribution can also be used for opacity, and usually is. This links out to a lot of really interesting stuff. I don't know if we're going to be able to go through all of them, but one of the ones that I thought was really cool was this game, Ecstaticus. It uses these, it's a rasterizer that uses custom primitives, these ellipsoid shapes, which I thought was really cool. And yeah, it's pretty unique for real-time stuff. This is from the 94, I guess, yeah, early 90s. So that's pretty cool. That's yeah, the so another piece here is the spherical harmonics. So that's the directional dependence of the primitives. So that's another piece that the neural networks are training there. learning, whatever. Optimizing the model for matching a set of photos, basically the same way that photogrammetry works. So there's a certain number of views of the scene taken as input, and then it's basically trying to optimize the set of Gaussian splats to accurately model the scene based on those known views. And so it's kind of a gradient descent thing to get closer to basically like those input images kind of being like the ground truth or whatever. So yeah, point-based rendering and stuff like that. It's been around since like '85. It was the oldest one that I saw linked here. But yeah, kind of interesting. There was some paper in here that was had some really cool pictures. That was I'm not remembering which one it is right now, but surfills is something we talked about not too long ago. That was disk primitives out in space for GI. Yeah, so there's a lot of cool demos that have used different types of splat primitives. A lot of these they're just kind of like just flat things in space. This one was pretty cool. It's just a bunch of circles. But yeah, modeling objects with them and stuff like that with by distributing them in space. Yeah. But yeah, so yeah, this we also went through this not too long ago. The I rewatched this the other day. I was curious about it. The rasterizing bounding boxes thing is pretty interesting. I want to mess with that. I saw somebody on the graphics programming Discord playing with that not too long ago for imposters, and I want to revisit that. But yeah, the tiled rasterization is the part here. So it's to render those soft edge blobs, basically. There's the order dependence for blending. So I guess the most straightforward way to do that is to write a custom rasterizer. Yeah, the author here has written a viewer for Unity. Yeah, so again, there's this links out to a number of really interesting things if you're interested in specifics. A couple of other really interesting aspects, and for actual usage, this is very important. The splats are actually very expensive primitives because they have to keep all the spherical harmonics coefficients. So it ends up being something along the lines of 250 bytes per, and some of these scenes you're looking at kind of millions of these things. So that gets expensive very fast. So one of the couple articles that this guy wrote, he was hitting on that aspect pretty heavily. Because all right, basically, first thing is you need to know position. That's pretty much a hard requirement. But then okay, extension on each axis is another aspect, and then the then you get into the spherical harmonics. And I guess you can strip off a lot of the higher frequency spherical harmonic stuff, and then you get something that's pretty close. But basically, then you lose a big part of why you would use this primitive. So he's looking at some stuff like reordering, kind of binning into spatial bins. I don't know, something along those lines. And then yeah, like some BVH kind of stuff or something along those lines. Morton ordering. Yeah, and then I thought this was interesting. He was so he was messing with putting it into texture data and then using block compression methods. I think this is maybe a little bit. Yes, he was just doing that to visualize, and then he's talking about using block compression methods to reduce the size of the data footprint, which is kind of interesting. So he had like a 12 times data footprint reduction there. So I guess that's good, but it does start to lose some fidelity if you look closely. You do kind of start to see those primitives get distorted. If my browser doesn't crash. Yeah, spherical harmonics. Yeah, that's something I'd like to get into a little bit more too. Specifically, how you, because I know basically it's kind of a if you're accumulating data into that or something like that, it's like you kind of have to have right, because it's like it's a collection of coefficients for like sine waves essentially for trigonomic functions for the directional components, but it's several different frequencies, and so yeah, you have to store all the coefficients for the different frequencies. So yeah, I don't know much about the way that the data actually is stored or manipulated. I would like to learn more about that as well.
The initial article talks about how the rendering is 2D Gaussians in screen space. I'm trying to get an
Right.
idea for what that represent. Like, how do you render 2D Gaussians?
Yeah. So I think yeah, like he was saying, basically he wrote a custom rasterizer for it because with the soft edges on them, you have that order dependence for the blending. So you got to do the depth sort.
Hmm.
But yeah, so that is some complexity. I think one of the ways to make that more practical would be along the lines of doing, yeah, basically, yeah, screen space binning. So yeah, just divide your screen up into some, set of squares, and then figure out which primitives fall into the squares as a first step, and then do a sort per square kind of thing.
Okay.
Because then you do front to back or back to front, however you want to try and do it. So I guess yeah, there were issues with the block compression. He was saying. Um, is interesting. Looking at the signal to noise ratio in the image. Basically to compared to a ground truth model. Yeah. Um, yeah, he's got a bunch of comparisons here, and varying levels of reduction here. The other aspects are or the other approaches you had. One of them was just removing the directional components, and I think you had some sort of video comparison somewhere in here, but it does remove the specularities and things like that. That's what you're getting from the. It's mostly the directional components of the lighting that you're getting from the spherical harmonics. So yeah, stripping that off makes it just a single color, regardless of how you look at it. So that kind of, it loses, however much it loses. Something I've seen a couple different demonstrations of. One of the things that it does with mirrors or reflective surfaces, they it'll actually learn the way that it optimizes that is it'll have like a space inside of the reflective surface where it's placing the primitives. Like old game dev type of stuff where they just rendered the scene again, flipped across the plane.
I think you gotta show a video because it looks so interesting.
The first Gaussian splat video I was shared was, and I didn't even know what I wasn't aware of Gaussian splats beforehand, was from the perspective of underneath the lake or like the pond. And so the camera flies up and out of the pond. And my brain melted because from the perspective of the camera moving, it looks like you're going into the water or out of the water, whichever it was.
Yeah.
It broke my brain.
It basically makes the like the virtual world of a mirror into a real world.
Yeah, it's really interesting. I don't think this machine is up to running any of these, honestly. But yeah, I would encourage people to check that out. It's very, very, very interesting. Yeah, because it's essentially, I noticed it on these reflective material ball things. If you zoom way in, you'll actually kind of like see the way that the reflection is modeled inside of the surface. It's, yeah, it's just really interesting. But it makes sense though, because if you have varying different views of these things, what does it look like? It looks like there's, the reflected world inside of there. So it makes sense that if you're doing it via gradient descent, that's kind of what it's going to arrive at. So the compression, a lot of the methods he was talking about kind of do reduce fidelity, but it's too long since I've used a trackpad. Yeah, here it is. I can't even run a YouTube video. 30 seconds. Okay, yeah, and so yeah, the surface of the water there. Okay, yeah, that's really interesting. Yeah, and it learns like a whole separate inverted model of the world, like underneath the water surface, because that's, I guess, what it kind of looks. I mean, that's a straightforward way to model it. It's really interesting.
It didn't help that I was seeing this in like a minified window, so it was really high quality looking because only at like full screen do you see it, the individual blurs and stuff. So I thought this was like a real camera, and I got linked in the middle of the video rather than beforehand, where they're moving around the entire thing. And so the fact that they're going into the water and this is what you see, I just my brain melted, as I said.
Well, it makes sense that it's lower fidelity in the reflected surface too, because it's maybe the water surface
Absolutely.
is not perfect smooth, and then it's also more distant, so it's got maybe less data to work with. So it's, yeah, I don't know, really, really cool stuff. And then it's even got secondary reflections inside the the reflection of the reflection on those top windows. That's really something. Because yeah, you can see like there's even stuff that's like behind the plane of that window. As you move the camera, you can kind of see how it like there's something even past that window. I think it's like trying to do the clouds and stuff in there. Yeah, really, really cool stuff. Yeah, but yeah. It's very, very similar to old game type approaches where the stuff was inverted across a just a plane, rendered the scene again, or I guess in this case, yeah, just fully duplicating the space there. So I think this one was mostly messing with that texture method, and then different types of formats and the effects on the signal to noise ratio. So yeah, over a gig for simple scenes like this kind of doesn't seem particularly feasible. You start looking at way too much data you're throwing around to represent something that's maybe not that high fidelity. But if you can get that footprint down a bit, I think that's more compelling. I don't know. Then he went and looked at so both and that's important both in memory and save to disk type of representations if you can get that worked out. So this one got into like VGA style palette usage. So the way that VGA graphics used to work, basically you keep an 8-bit value per pixel, and that refers to a table of 256 color values. So those color values in the table are kept at a higher bit depth, but the individual pixels only need to keep that smaller bit of data. So that kind of logic basically is kind of something you could try to. Okay, yeah, this is where he was showing the stripping off the spherical harmonics. So and honestly, some of these like it's interesting like how small an effect it actually has to strip off the spherical harmonics piece. I think you can definitely notice. Like I think the left is with the you see it particularly on the specularities on the bench the slats here. It looks a lot flatter in the one without. It's just the base color. And then on the table as well, you see, that it does look flatter, and it doesn't have the view dependence for the color as much. This one though is interesting. It did the reflections in the same way below the surface of the table. Yeah, how does the they've learned the ages-old trick of duplicating and mirroring the geometry for reflection. Yeah, so doing. Yeah, he's playing with this idea of keeping a limited number of distinct colors, and then each one just basically a number of varying number of bits to index into a table of sufficient size. If you ever remember, Windows 98 or whatever, if you went into the display management, you could pick like full color or 256 colors, that kind of thing. That's actually what this is referring to. It's the way that they used to manage color. 45 numbers per splat is a lot of data to be passing around. Okay, I guess sorting high dimensional data like that is difficult to. How do you cluster it? Okay. Yeah, and basically, yeah, just like finding the nearest data point, and then saying that that splat refers to that index in the table. And giving it a half precision floats gets that down a lot, basically. And doesn't lose a whole lot of fidelity either, which is pretty cool. Yeah, looking at up to like 20 times reduction in amount of data there. So under 100 megs from a gig and a half, which is pretty cool. Something, yeah, and then the last post in this has a lot more. This is the original paper that kind of brought everything to the forefront here. This whole concept. This 3D Gaussian splatting for real-time radiance field rendering. But there's a whole bunch of different stuff this has become a very hot topic recently. He wrote an editor. I don't know if I'll be able to find it's in here somewhere. Yeah, he wrote an editor where basically trimming these things to some bounds, because you saw before how it was like learning things that were like a block away. Thought that was kind of interesting. Basically, taking that data that it spits out and then trimming it down to a much more constrained set of primitives. Like you're saying, like, okay, this is good enough to represent the actual focus object, because you don't need the background or whatever it is. So I think that's potentially very interesting. So I don't know enough about this, but I think it'd be interesting then for how do you relate that kind of, because you're baking into it a lot of information about the surroundings into the spherical harmonics. So yeah, I'm curious about that, I guess. And I think another thing too is being able to manipulate the data format after the fact. You can do a lot with this. If the neural network training is kind of like an intermediate kind of thing, like it spits out some initial thing that you can then kind of manipulate after the fact, clean up, and put into some more usable type of, basically just kind of trim the parts that aren't going to be really relevant for your application. I think that's something that could help make this make a lot more sense. But there's no tooling for that really beyond just a couple of small tools like what he's building.
I do find it interesting. It's a neural network derived technique because it was only possible using differential rendering to generate the Gaussian splat data. But once you've generated that data, that's not a black box neural network only understands type
Right.
thing.
Yeah, that's big, because that's what NeurFSAR is. It's a neural network that you basically query with a direction to get the radiance value for that.
Yeah.
That ray through. Doing it in this much more straightforward format that is, transferable is really cool. Yeah. Because it is like a slightly more difficult primitive to work with than just triangles, but not crazy. Like it's not some opaque black box thing.
I mean, one could conceive of the nerf is just it contains all the Gaussian splat data just in a non like a I'm trying to draw a connection and I'm failing.
Yeah, it's a black box. Yeah, I
Yeah,
think,
it's a black box.
Yeah,
It's weird.
it's
I guess I'm just like it's weird you can pull the Gaussian splat data out of it, even if I know it's not pulling it out of the neural network, but rather it's generating the data using neural network stuff. But like the fact that you can encode Gaussian splats in a neural network is, interesting.
Mhm. Yeah, well, and I don't think that's what the internal format really looks like for the nerf stuff. I don't know what it does look like, but I think it's just something completely arbitrary. Like it's like one of those things where a lot of what neural networks are doing these days, there's no real way to reason about what it's actually doing.
Yeah.
So it's I think that's a little questionable. Some of the things that AI is being used for, but.
Yeah. Completely agree.
Yeah. But yeah, anybody have any questions or anything? It's a good range, yeah. So that's I think that's interesting, yeah, because some of those splats are like massive. Yeah, it's funny. Like you look at some of the ones that are on the G Splat viewer. It's interesting, yeah. Like there are, yeah, there's that single focus object that's in a very high fidelity kind of form, and it's the yeah, nice. We'll have to share this with some people actually. Yeah, but the lost my train of thought there. Oh yeah, right. So yeah, those very large, like low frequency details where it's putting just a giant one of these Gaussians out there in the distance. That's kind of interesting. It's right. It's learned that that's an effective. It's kind of hit a local minima there. That's like okay. That models that color out there kind of covers a big chunk of what's happening. But when you're you want to go and use that data for something, it looks a little silly. So yeah, I'll never be able to find the video again on short notice, but he had a video of basically drawing a box around the like the excavator when we looked at the just around the excavator, just a bounding box, and trimming everything, trimming the set of Gaussians to just the ones that touch that box, basically. So that's ones that are even partially contained by the bounding box, and then from there, basically eliminating all the other ones, and then further trimming that set down to just the ones that you want. So I think that would help make it more practical and put the concentration of data like where you want it. Kind of thing. Another one that I saw was animating these things. I noticed this was there, but basically being able to track motion, I guess, is like kind of interesting if you can move through. Totally obnoxious editing, but hey, what the hell? Yeah, just being able to have them follow a path or something in time is interesting. So if additionally you're learning some function for their movement over time, I guess is kind of what they're looking at doing. Rasterizing the splats, you could do it with a fragment shader. It's the depth sort aspect becomes a little bit complicated, maybe expensive more than complicated. I think most of what I've seen talked about is like writing a custom rasterizer. So it's just a compute process.